Yeah. So we did these first two examples last time. So today, 2 parts. First, we complete the remaining 5 examples. I hope I still have some time. Then I will go to the hint part. Okay, hints for your homework assignment number 1. So I just do a few questions. Yeah, definitely I cannot complete. So the remaining part, I will record a video tomorrow Friday. So I will record covering remaining relatively hard questions. Especially last 5 questions, I call challenging questions. So challenging questions, I will give you more hint information to help you do better. Yeah, let me turn off the slide. Yeah. Another thing, today, October the 2nd, Thursday, I want to remind you the midterm day. Yeah. Keep in mind, because now we are preparing us for the midterm. This homework assignment, number 1, it is targeting the midterm. Okay? The midterm similar questions. Homework assignment number 1. Midterm 2 weeks from today. 2 weeks from today. October the 16th. All right? 2 weeks from today. Yeah. Yeah. So that's why I want to remind you today. So help you, get prepared mentally, at least. Mentally first. Yeah. Otherwise, you get surprised. Yeah. If I do not remind you at least 2 weeks earlier, then when you come to the classroom Thursday, October 16th, suddenly we need to do the midterm, right? Yeah. So we don't want to see that happen, all right? Yeah. So the midterm still, recall in our first class, I gave you the format of the midterm. Part A, B, C, right? 3 parts. Yeah. Just to refresh your memory. Part A, online quiz. So you do it at home. Okay? So I give you 3 or 4 days. Yeah. You need to look at the syllabus. At least 3 days, 3 or 4 days to complete that. Just our normal quiz number 4. Okay? Yeah. Yeah. Because this week I will give you quiz number 3. This weekend you should have our quiz number 3, normal quiz. Okay? But quiz number 4, that is part A of midterm. Yeah. Same quiz format. Yeah. But we count it as part A of midterm. All right, that's part A. Part B, 10 computation questions. 10 computation basic questions. So that's what you are going to do in the class, part B. 10 computation questions. All right, yeah? In 75 minutes. Yeah. Part B. Yeah. After you get home, part C, online, 5 challenging questions online. So you have more time. Part C. Yeah. So refresh your memory. Part A, B, C, D. Yeah. So that's the structure. Yeah. All right. Yeah. So now you can prepare in your mind. Yeah. Do not get scared. Yeah. Now you have 1 week, right? 1 week for 1 week for deadline of the homework assignment number 1, right? Yeah. Homework assignment number 1. So when you work on it, you know you are preparing for the midterm. Okay? That's something important. Okay? because you're preparing for the midterm. Okay, homework assignment number 1. All right, yeah, let me stop right here. Yeah, because we have a lot of things to do today. Yeah, very easy. Yeah, so let me quickly complete it because we did a similar question last time. Our example number 1, we didn't have the exponent number. Yeah, n plus 2, f function, g function, m. Here, the only difference is that cube difference. Here, I only want to point out one important thing when you see a question like this. All right. When you work on it, do not expand the polynomial. Yeah. Because many students like to expand. So do not expand it. Yeah, because when I gave similar questions before, most students expanded. Yeah. Because if you expand it, it could be very complicated. Yeah. You need to use some formula, right? Yeah. A plus B, parenthesis cube, there is some formula. If you use formulas, you will have, oops. You will have things like this. N cube, what's one? Plus 6 n squared plus 12 n plus 8, right? Look at the expansion of this formula. Then when you work on this, is it complicated? Too complicated, right? Yeah. Hard to control. Yeah. So when you do it, the best way is don't do expansion. Yeah. What do? Yeah. So lower bound first. Lower bound, you remember, we just cross out that plus 2. So we can get lower bound easily. But for the upper bound, we use the same way we did in our example 1, upper bound. Replace 2 by n. To make the inequality hold, we need to add a range, appropriate range, some appropriate range. Then it's correct. Yeah. After that, then you raise to the cubic power. Okay? Yeah. You raise it. Raise to your destination power. Then no expansion. So you get a upper bound 8 easily. Yeah. So that's the main point I want to point it out. Yeah. In a situation like this. Don't do expansions. Okay? Yeah. Also, this expansion thing, in your homework questions, there are 2 questions. Remember? I ask you count the number of multiplications. Yeah, number 21, 22. Okay? There are 2 questions. Don't do expansions. All right? Same idea, because you mess up. When you do expansions, it's a huge expansion. Okay? You spend a lot of time, but you messed up the structure. If you do not do expansion, you keep the nice structure. Yeah. That's so beautiful, the structure. Yeah. But after you do expansion, you mess it up. Okay? Very messy. Nobody can control it. Okay? Yeah, so that's very important. Keep the nice structure. Yeah, it is useful to solve the problem. All right? Yeah, this point. So that's the first example. Yeah. So other things, very easy. Next one, example 2.4. Now we want to show log of n belongs to little o. Recall the meaning of little o. Little o of n. Little o. Yeah. Take the limit. Yeah. So little, the meaning is, yeah. So here I emphasize discrete variable because we are going to apply L'Hopital's rule. Remember, in L'Hopital's rule, we need to convert functions with discrete variables to continuous variable. Yeah, so here, before we go there, notice that discrete variable thing. All right. Then, because little o, we need to calculate the limit. Yeah. All right. So what is your goal? How to control? Yeah. All right. The goal, we want to show the limit. We want to show. Okay? Yeah. That's our goal. Yeah. But to show it, yeah, so in calculus, to show it, yeah, we connect to L'Hopital's rule. Yeah. L'Hopital's rule, you need to take derivative. Yeah. So then, in order to take derivative, yeah, because for functions with discrete variables, the derivatives are not defined. You cannot define derivative concept on discrete functions. Okay? Only must be on continuous functions. So we work on this continuous version, x continuous variable. So we have derivative well defined. Yeah. All right, next, before we apply the L'Hopital's rule, is there any special condition we need to check at this point? Some condition, we need to check it. Remember, a special form, indeterminate form. Indeterminate form. Infinity over infinity determinate, indeterminate form. Okay? Yeah, no problem, right? So after that, then we can apply the L'Hopital's rule. Limit derivative of denominator just 1. Yeah, very easy. Okay. Numerator, yeah. So you can find the formula. Okay. You search the web, find the formula. Yeah. So 1 over natural log of a. Yeah, base. Because here the base is hidden here. Here I assume we use greater than 1, not a 0, all right? Greater than 1. Yeah. Natural log of a, it's a positive number. When a greater than 1, natural log of a is a positive number. Yeah. All right. So that, do simplification, 1 over natural log of a times x. Here, another question. Let me ask you. Can we apply L'Hopital's rule second time here? Another time. L'Hopital's rule. Can we apply L'Hopital's rule the second time here? You feel okay? Check condition. What condition we need in order to apply L'Hopital's rule? Condition. I just asked you a few minutes ago. Indeterminate. Is this indeterminate form? Numerator, look at the numerator. Numerator, determined, right? It's constant 1. So it is not an indeterminate form. You cannot apply L'Hopital's rule. Okay? If you apply L'Hopital's rule, it's wrong. You get a wrong result. Okay? Yeah. So be careful when you apply L'Hopital's rule. check the form. So here we cannot apply L'Hopital's rule, right? So we take we take the limit directly. The limit, numerator, because denominator x goes to infinity, 1 over infinity 0. Yeah. So you have the answer immediately. Yeah. Yeah. If some students may argue, if I apply L'Hopital's rule, still correct. If I apply L'Hopital's rule, derivative of 1, also 0. So here you get the correct answer. It happens to be the correct answer. But the method is wrong. Okay? Because if in other situations you do in the same way, it's very likely you will get the wrong answers. So that's why we have to use the correct methods everywhere. Right? It's not, you only care about the result. You do not care about the process. The process, if the process is correct. So sometimes you may use the wrong process to get correct result. For us, we do not allow it happen. Okay? Yeah. So we want to make sure the process also correct. Yeah. All right. So then we can go back to the original question. So we replace the continuous variable to discrete variable, discrete variable by the limit of, the definition of limit. Remember? Definition of limit. Why we can, after we get this is our intermediate result. This is our intermediate result. After we get it, we can go back, So first we go back to this version, discrete version, then that version. But when we go back to the discrete version, why we can do that? We apply the definition of limit. Based on the definition, it tells us, and x approaches infinity in any way. Any way is acceptable. Now we take the discrete way. How about that? Any way is acceptable by the definition. Okay? Yeah. Now we choose the discrete numbers, 1 to consecutive integer, that numbers. Yeah, that's a special way. It is acceptable. Yeah. So when we do it, we get discrete version. All right? Yeah. So we complete a second example. All right. Yeah. Third one. Yeah. Next one. All right. Yeah, this one. Okay? This one related to our homework question. Yeah. Actually, the previous one, 2.4, also related to our homework question. But later we have another question. Yeah. So this one, power function, n to the d. D is greater or equal to 1 here. Yeah. Greater or equal to 1 here. But later, d, we require d just a positive constant. Yeah, not necessarily greater or equal to 1. The reason I put a greater or equal to 1 here, because I want to make the calculation relatively easier. Yeah, that's the only purpose. Yeah, easier. But after we prove it, then we can release. We can make this condition weaker. Yeah. All right. Little o. Yeah. Take the limit. We need to take the limit. All right. Yeah. But when we, all right, so here, let us review our problem solving. I gave you some problem solving method before. Here I want to use this question to review that method a little bit. All right. In the original question, d is not required to be integers. D, in the original question, it could be any number greater or equal to 1. Okay? Not necessarily integers. Yeah, that's our original question. But when we work on it, now I want to assume D are integers. D, all the d values are integers, I consider that case. Do you feel we can do it in that way? We assume d are integers because that's easy. Yeah. We can do that. Remember, we always work on the easiest case first. Okay? Although at the end, we do not require the integers, but can we work on integer case first? Right? So that's the easiest case. So our first case, we assume d must be an integer. So let us prove it. After we prove it, then we consider non-integer case. How about that? Right? Yeah. Then we consider non-integer case. Yeah. In that way, we can solve the problem better. Yeah. All right, let me show you. When d is integer, why d? When d is integer, it is more friendly for us. When d is integer, it is more friendly for our calculation. Because when we take derivatives, is it nice? Yeah? When the exponent number d is an integer, when we take derivatives, so nice. Yeah, right? Yeah. So that's the main reason we like the integer d. All right, so let us do the work. Let's calculate continuous version of the ratio. Yeah. And here, we need to apply L'Hopital's rule. But when we apply L'Hopital's rule, check the condition. Indeterminate form. It's okay, right? No problem. Indeterminate form. So we can apply L'Hopital's rule. All right. Let's apply the first round. Yeah, the first round. We take derivative. Take the derivative. We need to use the derivative formula for the numerator, denominator. Numerator, we use the power rule. Remember? The power rule. This formula we call the power rule. Okay? D times x to the d minus 1. Denominator, yeah, you need to find the formula, right? Yeah. All right. Then, after we take the first derivative, we get this intermediate result. Can you see the answer? Yeah. Still hard, right? Still not that obvious. The answer is still not that obvious, right? Not obvious. Yeah. You can see the answer, this intermediate result. Other than the constant part, you have some constant part. Okay. If we take out the constant part, we just look at the variable part, similar to the original form, right? The only difference, d is changed to d minus 1. That's the only difference. Okay? The form is the same. Yeah. It looks like we are in some cycle, right? Yeah, we are in some cycle. After we do one round calculation, we get back to the form similar to the original form. Okay? Yeah. It looks discouraging, yeah. but not that bad. At least we do one thing, one improvement, because we reduce the exponent number by 1, right? Yeah, that's the progress. We reduce the exponent number by 1. Do you want to reduce the exponent number more? Right? More, right? Yeah. Let's do more reduction. So we apply L'Hopital's rule another round. L'Hopital's rule, because it is still, yeah, think about if d is greater than 1. Yeah. Here d is unknown. Yeah. Imagine if d is greater than 1. It is still indeterminate form, right? Yeah. So we can still apply L'Hopital's rule. Let us apply L'Hopital's rule the second round. Yeah. All right. Okay? Yeah. by power rule, then by derivative of exponential function, another time. Yeah. So you see, your constant part changes a little bit, but the variable part, you bring down the exponent number by another one, d minus 2. Yeah? Although in this way, you may wonder, when can I get to the end, right? Yeah. It looks like, keep doing this forever, yeah, but not that. Yeah. Because we know d is a fixed number. D is fixed, right? D, you cannot change d. After it is selected, it must be fixed. It's not like x. X is a variable, but d must be fixed. If d is a fixed number, then when we do reduction like this, sooner or later, we can reduce the exponent number to 0. To 0. To 0, it's gone. Right? Exponent number disappears. So our goal, we want to reduce the exponent number to 0. Yeah. So there is a hope, right? Yeah. Because under certain number of rounds of reduction, we can reduce the exponent number to 0. Then it disappears. Disappear, that means numerator, the variable part becomes 1. That's nice. Okay? Let's keep doing things. After we do multiple rounds, certain number of rounds, yeah, at the end, the numerator function becomes variable part x to the d minus d. Okay? We do d times, right? D times. So reduction by, by d. Yeah. D minus d becomes, so the variable part is gone. Yeah. This time, it is not indeterminate form. It's not an indeterminate form anymore. Then you can calculate the limit directly. When x goes to infinity, the denominator goes to infinity, the whole fraction goes to 0. Denominator goes to infinity. Numerator, constant number. D factorial. D factorial is a constant. Constant over infinity, yeah, 0. So you find the value, 0. Then you go back to, so just a minute, So because you have the continuous version, then you can go back to the discrete version. So when you go back to the discrete version, you have you have this. Okay? You have that. All right? Yeah. So you prove it. Yeah. All right. Then, remember, we just proved the easiest case, right? Yeah. Our goal, we want to prove the general case. The general case. How to prove the general case? General case, d may not be an integer. D could be non-integer. Now, remember, so now we need to recall the method I talked about a lot before. All right. In this situation, what is the method? What is the strategy we want to use? Strategy. Non-integer and integer, how close they are. What's the difference? The difference between integer and a non-integer, is that difference big? What's the difference? Small difference, right? Integer and a non-integer, the difference is small, right? Yeah. All right. Then, we already have the result of the integer version, integer D version. Can we use this existing result as a stepstone for our non-integer case? Can we use that as a stepstone? Because we have it. We should use it. We do not want to waste it. Okay? So we use it as a stepstone to lead us to the destination. That's the strategy. Okay? That's the strategy. All right. So, but this time, we only need to work on the difference part. There is a small difference. We only work on the difference part. All right. So what's the difference part? All right. Yeah. If D is not an integer, D is not an integer, can we approximate by an integer? D is not an integer. Do we have can we use the ceiling function of D to approximate D? Ceiling function. It's an integer ceiling function. But it is greater than D. Okay? It is greater than D. It's an integer, and we have the integer result. Yeah. Can we use this special case as the stepstone? Stepstone. All right? Let me show you the stepstone step. All right. All right. The key formula I want to give you here. All right. This is our original form. Now, we do special transformation. Transformation, okay? Yeah. When we do transformation, we use a special structure. The structure information, very important here. So what kind of structure? Yeah. I split the original fraction into two fractions. Yeah, let me show you how to split. The first fraction, how about that? N to the D over N to the ceiling function of D. Ceiling function of D. Okay, all right. Second fraction, N to the numerator, same function, denominator, N. Can we split in this way? Can we split in this way? Yeah. Right? Yeah. Cancellation. If you do cancellation, you get back to the original form. Yeah. But this split reveals some special structure we can use. Special structure. All right. The first fraction, ceiling function of D is greater than D. Do we have this fraction less than 1? Yeah. The denominator is greater than numerator. So that function value always less than 1, right? Yeah. Yeah. Okay? Yeah. So the first fraction less than 1. What is the limit of the second fraction? We just did it, right? We did it. That's the integer case. That's our integer case. But that limit is 0, right? Yeah. Based on our first case, so this limit 0. Limit times a number less than 1. Is it 0? When you take the limit, okay, yeah. When you take the limit, one limit we know it is 0. Another one is some number less than 1. You multiply these two numbers, 0. Okay? Yeah. So you prove it. So for the general case, you can use this way, you prove it. Okay? Yeah. So here, the strategy, let's review that strategy. Bridge the gap. Okay? Yeah. Yeah. there is a gap. Yeah. Yeah. Your original problem, you work on a simpler problem first. Okay? The simpler problem, when you compare it with the original problem, there is a small gap. So you need to find a way to bridge it, that gap. Okay? So then you complete it. Yeah. So this problem-solving strategy, okay? Yeah, try to learn it. Yeah. All right. So we complete this example. Next example. Yeah. So this time, log little o root of n. Yeah, root of n. So actually, we did a similar question before. Yeah. Yeah, remember our example 2.4. We do not have that root. Okay. Yeah. We do not have that root. Yeah. All right. So here, for this root, yeah, actually the way we do it similar. Yeah. So that root function. So we work on the continuous version. The root function, we can write it as the 1/2 as the exponent number. Yeah. 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 It's okay. Yeah. No problem. So we use it. All right. Then we can apply L'Hopital's rule. Yeah. It is an indeterminate form, so we can apply L'Hopital's rule. Yeah. Yeah. The denominator, we use the power rule. Denominator, power rule. Yeah, remember? Yeah. Power rule works for this kind of power function. Okay? Yeah. That kind of power function. Exponent 1/2, we can still apply the power rule. Yeah. All right. After simplification, it is not in determinate form anymore. Yeah. So we can calculate the limit directly. Okay? Yeah. Yeah. When x goes to infinity, it is 0. It is 0. Yeah? Then we go back to the discrete version. Yeah. So we can get a conclusion. All right? Yeah. Yeah. The last example of this part, yeah, 2.7. Show that natural log of n belongs to little of n to the d. D is any positive number. D greater than 0. Yeah. So that I want to show it. Still a little bit as well. Okay? All right. Yeah. Continuous version. Yeah. All right? Yeah. It is an indeterminate form, so we can take derivatives directly. Yeah. Derivative of the numerator function 1/x. Derivative of the denominator function, power rule. We can use the power rule. Yeah. D times d to the x to the d minus 1. Yeah. Power rule. Then simplification. Let's do simplification. After simplification, we get this form. It is not an indeterminate form. Now, then we just do the limit directly when x goes to infinity, because d is a positive number, so x to the d must go to infinity. Denominator must go to infinity, so 1/infinity, it is 0. Okay? Yeah. So then we can go back to the discrete version. For the continuous version, the limit 0, so then by the definition of limit, we get the discrete version. Yeah. All right. Yeah. So that's all these examples we need to learn regarding the asymptotic notations. Yeah. All right. Then let me do summary on these questions. Do summary. Yeah. Yeah. This time, I try to connect to our homework questions. Homework questions. Okay. All right. All right. I want to use two examples to connect to our homework questions. The first one, this one, okay? The second one, this one. These two results. Yeah. After we prove them, we can use them as our results. Okay? Yeah. So here, I want to explain. Yeah. When we use these two results, what is the right way to use? I want to explain that part. Yeah. All right. First, let me explain the first case. Yeah. This first case, n to the d belongs to, we know, a greater than 1. Okay? It's true, right? This result must be correct whenever the condition is satisfied, right? Yeah. All right. The condition, what's the condition? One condition is A must be greater than 1. Second condition, D must be positive. 2. Yeah. That's the conditions. Yeah. Yeah. Yeah, but the D negative, we know, we do not consider that because D negative, the first function goes to 0. Okay? Yeah. So D is positive, so the first function goes to infinity, right? Still, we can compare, but it goes to 0. Too trivial, right? Too trivial. Yeah. Yeah. It does not mean D negative it's wrong. Yeah. D negative also correct, but too trivial. Okay? All right. So here, the question. When we apply this result, sometimes, because when we work on the question, sometimes we use our intuition, right? Our intuition. Yeah. So your intuition may not be reliable. Think about your intuition. Your intuition may not be reliable. Yeah. Something you feel correct, but it may not be correct. That happens a lot. Yeah. Here, I want to show you that situation. So you feel, this is correct, but based on scientific result, it's incorrect. That could happen, right? Yeah. Here, I want to show you that point. Your intuition. Yeah. Think about your intuition. Yeah. N to the D, we only require D is a positive number. So we have freedom to choose D. Right? We have a lot of freedom to choose D. Okay? Yeah. So here, I can choose D like this. I can choose D like this. 1, 0, 0, 0, 0, 0, 0. How about that? 1 million. Can I choose D 1 million? Yeah. N to the 1 million. Is that a big value, large value? When n is very large, because we make n go to infinity, right? N is supposed to be very large. Then we raise to 1 millionth power on a large number. How large it is. Okay? Think about that. All right. That's the first function. Now we compare it with the second function. Second function is exponential function. Exponential will only require a greater than 1, right? If a is greater than 1, then it is acceptable, right? Yeah. That's the only requirement we need for a. Yeah. Now I follow your rule. A greater than 1. I do not violate it. Okay? All right. So I choose A. 1.0000001. It's greater than 1, but only with some tiny bit, right? The difference is so small. 1 millionth. I only add 1 millionth on 1. So you know it's a very small number, right? Very close to 1. Okay? All right. Then I raise, because a to the m exponential, raise it to nth power. These two functions. Now I ask you to compare these two functions. When n goes to infinity, which one is larger? When n goes to infinity, which one is larger? Think about that. Think about that. What? Equal to, both go to infinity. Yeah, that's no problem. Both go to infinity. Okay? But when two functions go to infinity with different rates, right? Some with faster, higher rates, some with relatively slower rate. Okay? Now I want to ask you, which one goes to infinity faster? Faster. That exponential one. Other students, do you feel the exponential one? Oh, you feel? But 1.0, so close to 1. We know 1 to any exponent number is 1, right? 1 to any exponent number is 1. That number, although it is slightly greater than 1, but we raise it to nth. Do you still have confidence this function eventually it will dominate the other big function? Do you have the confidence? Gabriel, do you have the confidence the exponent will dominate?
Yeah.
Good. So, Jonathan, how do you feel? Yeah. Great. Yeah. Because you trust this result, right? You trust that this is the result. We just did it. Yeah. But if you use your intuition, it's not easy, right? Yeah. By intuition, we may feel the first function should be much larger. Okay? Yeah? Because I remember one semester, one student showed me use some online graphic software. Yeah? Because some online software that can draw graph of functions. Right? Yeah? When you enter a function formula, then you draw the graph. So that software can show you the graph. Yeah, very easy to find that. But when that student apply that software on this question, the software tool does not help. The software does not help because the second function greater than first function, it occurs very far and too far. Okay? The software cannot show that big range. Cannot. Okay? If you cannot reach that far, you cannot see the truth. The truth occurs in a very far universe. Like that. But you cannot reach there. Yeah. But this result must be correct. Yeah. So use the graphic tool, doesn't help. Okay? Yeah. All right. That's the first example. Second example. Second example, this time, natural log of n to the d. Okay? Yeah. We know this result must be correct. We just prove it. Yeah. We proved it. Now, we want to understand. Okay. The D here, we only require it is positive. That's all we need. Okay? Yeah. So based on that requirement, so this time we follow that requirement. So then we do comparisons. Yeah. This time, when we do comparison, yeah, the first function, this log function. Okay? The second function, when we do comparison, n to the d, yeah, we have freedom to choose d, right? We have freedom to choose d. No? We only need to choose d greater than 0. Yeah. How about we choose d very small, 0.0000001. This small. How about that? The exponent number, very, very slow. Here, I use 1 millionth. Okay, 1 millionth. So small. Okay. Then, when you compare these two functions, we know both functions go to infinity. Yeah. But when n is very large, approaches infinity, which function eventually will grow faster than the other one? Which one? Yeah. Get an idea? First one or second one? You feel, yeah, still, you know, you have confidence to say one of the two functions grows faster. Yeah. Yeah. By this result, yeah, so if, yeah, even if this d very small, by this result, the second function should be larger, right? Yeah. Little o means log function. When you compare with the, you know, the g function, yeah, let's say g function, n to the d, the limit is 0. When n goes to infinity, the limit is 0. Yeah. So the first function, when you compare with the second one, because the ratio, the limit of the ratio will be 0, that means the second function eventually will dominate the first function. Dominate like with the infinity times big, that big. The dominance is infinity times that big dominance. Yeah. But that's by our second result. Okay? All right. So here, I want to address the point. Yeah. If you want to make your decision by your intuitions, okay? Intuitions. Yeah. So for these two questions, yeah, sometimes your intuitions may tell you different ways. Yeah. Now, your intuitions may favor, yeah, it's very likely, your intuition may favor the first functions. Yeah. Think about, if you do not learn this section, if you do not learn, if you answer these two questions directly based on intuition, it's very likely you will choose the first column of the functions. So you will favor the first column of the functions, right? Yeah. By your intuition. Yeah. Yeah. So that's the point. Okay, all right? Yeah. So after you get this explanation, now there are, as I remember, there are 3 related questions in your homework assignment number 1. So I hope you can answer those 3 questions with confidence. Apply these 2 results with confidence. Right? Yeah. Yeah. So last 5-something minutes. Yeah. Yeah. So here. Yeah. I cannot talk. Yeah. So I prepared several questions, but here I can only do one question. Hint for this question. That's question number 15, our homework assignment. Yeah. All right. Yeah. So I think you are familiar with the question, so I do not need to read it again. Yeah. But here I want to point out. Remember connecting the dots. Okay. So here the first thing we need to do this. Connect to the dots. The first big dot, I would like you to connect the big dot. Finding the minimum of an array. Okay? Yeah, that's the big dot you need to come. Related to this question in some way, yeah. Big dots, we know the answer of this question, n-1. Yeah. Yeah. So here, n-element array. Okay? N-element array. Yeah. So the answer is n-1. All right? So we have this result. Now, you use the same thinking, yeah. So because you need to go through a sequence of deduction, logical reasoning steps. Okay? Yeah, you need to go through. Yeah. All right. So here, I hope you using the same sequence of logical reasoning steps to answer this question. All right. So this question, yeah. Now let me write a general version. General version, given an element array. Okay. We need to find minimum number comparisons to find an element. Yeah, because it could be you can have multiple solutions, but we only need to have one of the solutions. Yeah, so one of the many solutions. An element among the top k, among the top k values. Okay, among the top k values. That's the general version, right? Yeah, because here you only change n number. Your n in this question, 479, your k number equals 8, right? You only use some concrete numbers here, all right? Then, but when you connect to finding the minimum question, so you have n element array, the minimum question case, that k equals 1, right? Top 1. Okay? Oh, minimum. Oh, yeah, sorry. Here, the minimum version I replaced by maximum. Okay? Yeah. Because that's more convenient. Maximum. Maximum means top 1, right? Yeah. So here the difference is only the k number. That's the difference. Yeah. 1 and 8. Yeah. All right? Yeah. K number different. All right. Then, yeah, so, yeah, close to the end. So I just say a few sentences here. Yeah. When you solve the k equals 1 case, the main idea is the winner needs to be eliminate n minus 1 elements, right? The winner needs to be eliminate n minus 1 elements, okay? So by the elimination method. So here the main important is elimination method. Elimination method. All right. And here you get to this question. You apply elimination method. You need to eliminate the winner, the solution, the possible solution. Okay? So this element, the solution element, okay? Eliminate. Yeah, sorry. Eliminates. How many? Think about. Top k. Top k eliminate n minus k elements, right? Okay, if you can find some element that can eliminate n minus k elements, then that's a solution, right? Yeah. So using the same logic reasoning, thinking, okay? Yeah. Then you can solve it. Okay? All right. So let me stop right here. Yeah. The remaining questions, yeah, whatever their number, 6, 7, 8 questions, hints, I will record a video. Okay? Yeah, post by the end of tomorrow. Yeah, by the end of tomorrow. So then you use this weekend. Yeah, because this weekend, so that you have relatively more time. Yeah. Try to do as much as you can. Yeah. Homework assignment number 1. All right, that's it.